Sunny, and today I want to explain you how we can match the stars with Gaia DR3 or Gaia Data Release 3. I can share my screen now. I want to do it for this class OC0623, which I observed with Danish telescope. And if you remember, or if you watched, or if you didn't watch, please, if you want, you can watch the videos that I explain you how we can how to do the photometry in IRAF. If you want, you can watch it. I recorded. It is available in my page, and in my channel you can see it how to do photometry in IRAF. So I did the photometry for all of my observed clusters, around 200 open clusters. I observed them with Danish telescope in Chile, DK 1.54. And then I did the photometry for all of them. And now after that, I matched the stars of them with the Gaia DR3, and I finished the matching with Gaia. And now today I want to explain you how we can match the stars with Gaia DR3. And I chose one cluster with the name OC0623, and I want to match it with Gaia. And I want to show you how you can match the stars with Gaia. And this is from 0 to 100. You can, if you do not know anything about matching with the stars with Gaia, you can watch this video, and then you know the whole progress. So just please, before you should do the photometry for this cluster or any clusters that you have, and then I create a folder with the name for matching, and then these are four, and but before that we should do this. First, you should copy the two files with the name U and U underline Mac. As you see, we have it here. Let me. Yes, I can now better see it better. So we need these two files. U that fits on U underline Mac. If you remember, you can have them from photometry. And then I copy them and paste here because we need them. And then as you see, from this structure, I do it from this structure. Instruction, then in the command line in terminal in Ubuntu or Windows, you can write this command: cut minus F and 3 minus D and then the name, or before, just remember, before that we should specify where we work. So I write the address, city, university, and problem, OC, and then for matching. So we are in the directory, and then we write this command, this one here. Cut minus F1 3 minus D, and then the name of the cluster. I will explain you what I'm working. So we check it, cut minus F1 and 3 minus D quotation OC, the name of the cluster underline MAC is greater than U underline XY dot txt. So what this line means, it means that we want from this file that we have it, U underline MAC. Let me show you what we have in U underline MAC and also in XY. So in U underline MAC, as you see here, we have these 5 columns, and they are right ascension, declination, magnitude, and XY, and the X sky and Y sky. And from here, we want to cut from the column 1, 2, 3. From 1, 2, 3, it means that 1 and 2. Because when we say 1, 2, 3, it means 1 and 2. Sorry, because of the sharing here, there's a panel and I cannot see and do. So I should do something like this. Okay, it's better. We should cut or extract the columns from 1 to 3. So 1 and 2, we need it. We extract these 2 columns into the file xy.txt. And this minus D means it is the delimiter. And it wants to how to separate the columns. And for separation, we use space. As you see in the columns, there is just a space. So here, as you see here, there is one space between each numbers. Then we have this greater symbol, and it means that it should extract the columns of 1, 2, 3. It means 1 and 2 with the delimiter space from the file u underline mac.txt, and then it put it into the, it is somehow like arrow. Then it goes to the output with the name xy underline txt. So u underline mac is our input, and u underline xy.txt is our output. As you see here, we just have one right ascension declination in 2 columns with space delimiter, or it's separated with space. And then we go back to the terminal. Here we write IRAF. We should go to IRAF. So sorry, I should rename it because it doesn't accept the space. So I think now it's okay. Yes. Now we go to IRAF. We open IRAF here, and we write rotate, and the name of the cluster OC, U underline fits, again O, U underline rot, that fits. And here we see 270. What does it mean? So keep this line here, and I will show you what does it mean. You see, we have the coordinates of the cluster. This is the alpha and delta, or right ascension declination of each cluster. And for OC0623, the right ascension declination is in hour, minute, and second, also degree. But we need it in degree because we want to copy and paste in the software with the name Aladdin. So we have this, and then we go through until here, around 15 cross 10, and then we open the image that we took in, and we observe it with the Danish telescope. And here, Z scale, Z scale, because we want to see how it is. Okay, and now we see that we should correspond the sky here. Already shows the sky for us, the sky, and then we want to see how it is in our observed image. As you see, we should have one brighter star here, and then this one here. Yes, in somehow in one line. But here we do not have this. So maybe it means that our image has some rotation. It should have it. Then we rotate the image in 90 degree. No, the star is here. 180, no, it is here. The star should be in the up. And then we rotate it 270 degree, and then we see, yes. You see, this is the brightest star, and then this, and then this. And between them, we have these two here. Also, we have these two as they are here, and then faint star here. You see, it is somehow correspond to the sky. Now, you see, here we have this 3 star here. Yes, and then 2 star here, and 1 faint star, and then 1 star here. So this is the image that rotates. So we should rotate our image in 270 degrees to show the exact degree in our sky that we have here. So this is show that the frame should have 270 degree rotation. So in IRAF, as I told you, you see, so we have 270 degree. Again, we check it, rotate the name of the cluster, U underline fits, U underline U that fits, and then underline U underline road that fits, and 270 degree. What does it mean? It means that we rotate the image, this image, U on the underline U that txt, this one, from 0, which was this, from 0 to this image, this one, in 270 degree. You see, they have different rotation. This is the original one, the U, and this is the U underline rot. You see that it has 270 degree rotation from this one, and it shows the real sky. Here it also means that this image rotates in 270, and this is the U underline rod that fits is the output, input and output. So here we rotate them, and then here back to command line in IRAF, and then we write WCS tools. What does WCS tools means? It means that WCS means World Coordinate System tools. And with this, we go to XY to sky, as you see here. And we write XY to sky minus DH, the name of the cluster, U underline rod, ampersand, name of the cluster, underline XY to sky, greater than, also U underline AD dot txt. And here, you see what does it mean? XY to sky minus DH, OC underline rod, ampersand, OC underline XY dot txt, greater than U underline AD. It means that we want to change our coordinates because the coordinates of our image is different from the coordinates of the sky. So we want to change the coordinates of XY, our image, to coordinates of the sky, to sky, and it reads from the header. It will write from the fixed header of the of this cluster, and this ampersand separate from the input file that is xy .txt, and the output or the result goes to the file text file with the name u underline ad.txt. So we have the file u underline rod, this image. It reads the head fixed head of the this image, and the input file is xy to sky, and you see it changed the coordinates of this, right ascension and dictionary of this, and then it goes to this result with the right ascension and declination, that it changed from xy into right ascension and declination of the sky. You see, here are from xy to sky. For example, the first one, as you see, these are xy to sky, and it changed it to the coordinates of the sky, and with the name right ascension and declination. So, because we need from the sky coordinates, because we work with the sky coordinates. So, and then we should use the file ad.txt and show you. And the thing is, one point is because of observation had some our software of the observed clusters that we use for Danish telescope had some offset from the Danish telescope. We found that the offset is for X or right ascension, it has minus 0.0020, and for declination it has the offset with minus 0.2340. So we should apply this offset to the coordinates of AD.txt. So for that, I do this, copy, and then I paste it into the Excel file, and here, here, here. So here, we see this. And I apply this offset in here in Excel file. Also for this one, for declination. Because my laptop is too hot, I close some program. Also this one. Oh, Passion code AB. Then here, in Excel, if you drag and then you do this, you have it for all of the numbers. Again, for this column, for declination. So now we should use the magnify because we need the magnitude. In the AD.txt, there is no magnitude, but we should use it from the magnify. And I copy and paste it here. These are not much important. I do this because some numbers are in right or left. And this is the magnitude. So now I copy the this offset number and also magnitude, and then I paste them in new Excel file and change the name of them to right translation and declination. And then I copy we'll paste in the text file. We have 176 stars from this cluster. So now I save it. Here with the name, right ascension, declination, and mark. .txt. And so the Excel file. and I save it in CSV with this file because I need it in CSV for matching the coordinates and magnitude with the Gaia. It should be in CSV format. So I save this file in .csv. And the last one, I save it as usual format in the same directory. So I do not need this. I just need this one, which I save it. Okay. So I do not need this. Also this one I do not need it. So I just need this file now. So I go to this web page in this year. If you open the Simba and then you go to Vizier, and then you can go to Xmatch directly. And here you see the Xmatch and table magnitude management. And here you see that we have, we should open the file here. This file, the right ascension mac definition mac.csv, and then upload to the store, and then we go to the Xmatch my store because we uploaded. It is not from Vizier or Simba. It is our file which we uploaded. So we go to the my store, the file, and then we search here from Vizier. Gaia DR3 EPA 2016. It has 176 rows, and here you can choose from 2 arcsecond to 10 arcsecond, but I use 10 arcsecond because I want to see more stars, and then I reduce the stars. So not worried about this 10 arcsecond. And then begin the X match, and then it asks you that which columns you want to match, right ascension and declination. For magnitude, it match it. It doesn't need that you mention. Okay, here it start to match. So it takes a few seconds, so fast. And then I also again downloaded as a CSV file. Here, this is the file. So now here we go to this 4 program, which I wrote them in Python, and you see I upload them here in Python. Again, I think I should use this one here. It's better. Okay. So we need this for program for matching, which after matching, which I explain you about them. So We should write in the directory that we want to be. Just be careful that the address of here and here in program and also in command line, it should be the same. They should be the same. As you see, OC0623, OC0623. And then what does it mean? I will tell you just a second. That we copy this one and then paste it here, as you see. And then I open another one with the same name, but again, this one is CSV. I will tell you the difference between them. I just should, okay. So from this file that we matched it with Gaia, we need these columns that I tell you. We want to copy right ascension, declination, magnitude of our observed data here. These are from us, right ascension, declination, mag from the file that we uploaded in Xmatch. So I copy and then paste them here. And then we need the right ascension declination from Gaia. These are the other ones are all from Gaia. Copy and then paste it here. And also we need angular distance. And please be careful about the order of them. They should be in the same, in this order. Not different, for example, not say that, so okay, I copy from here to here. No, it should be as I tell you. At least if we want to follow my structure. So then G mag, BP mag, and RP mag, these are from Gaia. And at last, we have DR3 name here, and copy and paste it here. And from here, you see it runs for DR3, Gaia DR3, and the numbers. But in programming Python, if you write like this, if you have like this, it has some error because it cannot specify that this is a string or float. It should be all the same. So we remove the Gaia DR3. We replace it with nothing because we do not want anything. And then you see that some columns of G, BP, and RP, they are nothing. So they are not useful for us because we need the magnitude of the Gaia. So then we again remove these columns. And if you remove these columns, how you can remove them? You should first replace it with 0 as I do this, and then we remove them. And how we can remove these columns that they have 0 from this line file, as you see, because it is too hard for around, for example, more than 200 clusters, you want to remove them one by one, it is too hard. So I just save. I just save and then close this one, but we need this one, so I save it. And so I wrote a program for this, that how we can remove this with this program. What does this program means? It means that from this file, it's read from this file. So we have removing underline matching, that's CSV. This file, so it's read from this file, and you see in this file that we have a lot of zero or nothing, and it writes that if remove the delete the rows that the Gmail, BP, and RPMac are 0, and then save it in the file with the name after underline matching .csv or after underscore matching .txt. I write it into format into CSV and text file, but you can have it in text or CSV, no difference. So I run this program with here, as you see, it writes run Python file. I save this one. Yes. Because here I put underscore. Okay, and now we can run it. You see? Okay, and what is the result? The result is in the file after underscore matching .txt or text file. Here, after matching .txt, as you see, yeah. You see, it's date from it has 1,123 from 1,285, and then I have this program, and here, for example, I can show you. But I want to explain you what does this program mean. Let me show you that yes, after matching, yes, I have after matching in here. Yes. You see here, for example, for example, this one. You see here how many we have. This one, 1, 2, 3, 4, 5, and 6. Because in matching we have some repeated matching that it repeats some stars, and we want to remove them because we do not want again the same stars. So for this, we want to remove them, and how we can remove it? You see, for example, here we have 6 stars with the same right ascending. They are 1 star actually. These are 1 star, but in different with the same as you see, the same right ascension, declination, magnitude, all are the same. So it is 1 star, but it's repeated. And how we want to know that which one we want to use? We use it from the angular distance, and we choose the least angular disk. So we choose the first one, and this program here said that from we have this file, this from the after on the matching.txt, this file. From this file, it remove or delete the number or right ascension definition and the other ones from here, and it remove them and just give us the right ascension definition magnitude and this GB, PRP, and DR3, which has the least angle disk. And then it put it as an output to the file after underscore matching underscore result.txt. You see when I run it. Okay, again I should do this. Okay, I mean that I should do it for all. But I won't have problem anymore. Okay, you see that I run the program. Yes. And then here you see, for example, the first line that it removed the repeated stars, and then it gives me this file as an output. For example, this file, you see that we had this file with 6 repeated star here, yes? And we said that we want the least angle disk, which is this one, the first one. So just remember 5 angle disk, 20, 21, 20, and 5. And you see here, this is that star here. So you see the program works well. Or for example, this star that's repeated several times. 1, 2, 3, 4, 5, 6. 6 times it's repeated, and we want to have the least angular distance, which is from this criteria. And if the program said that if right ascension and declination are like each other, similar to each other, then look at the angle disk and then choose the least angle disk, and then write the rest of them, the G, BP, RP, and DR3, which are related to this least angle disk. You see from 2 to 3.19079, and the least angle disk is 2.6, and then we have G, BP, RP, and DR3. And here you see this is the star, and the least angle disk was 2.6, and then the rest of them, it prints them here. So the program works well. And then we want to see that how many stars of us, which we had it here, we had it here, match with Gaia. Here you see we have 177 column or 176 stars, because the first row is right ascension, declination, match. And so from 176, how many stars matched? You see after matching. Yes, the same 177 with the first column and here. So it matched 100% of our stars. So it means that exactly it matched all the stars of our image of our cluster with the Gaia DR3. So it's perfect. So great. And then we close this file, we do not need it. And then we go through this program, this file, as you see. I will tell you what does it mean. I just, instead of writing in two different files, I wrote the program in one file. This one means that from file after underscore matching underscore result.txt, which was this file. It's read from this file, and it just we want just the magnitude, mag U and G mag, BP and R mag. So we just separate this four magnitude into a new file with the name text file with the name mag G BP RP. As you see here, oh, I should run it. Okay. After my okay, after matching result.txt. Okay, there's a problem line. It seems that something went wrong. Okay. Oh, the directory is not correct. I should remove this one because we should be in the correct directory. As I told you, it is so important. So now it works, yes. Yes, I have also this one here. Okay. Just pay attention that you should have the correct directory because I had something wrong here. Then because I had it from the previous file that I had, I copied there from there, and then it had problem. So now we are in the correct directory. You see. So I open Mac G BP and RP, and then I copy and paste them in the Excel file. I remove this because we do not want to separate them. Okay, and then the next one, G, yeah, Mac G BP, and the last one, RP. And then I add insert them, and then put them here. Mag G BP and RP. So okay, I just do this for myself. We can also do this if you wish. Okay, and then I copy and paste it in the text file. I just do this, but it doesn't need. If we want, we can do this. Okay, and then I do this. I back this program because we do not need this. Just be careful about the directory. And then I copy the name of here. Yes, Ph.D. And I copy and paste it here, but in the directory here. Also, I save this file in the same directory, you see, with ODS format. Also, I do this because I want to have another tab. I just do this for myself to have separate them, to find them after a while better. It is for this. It is useful if we have a lot of files, you can find them better. So then I use this, and then I have this file. So I told you that this program said that we just want to separate MAC, GBP, and RP from the file after underscore matching underscore result.txt. We just want these magnitude files. Then we separate it and put it in the text file with the name of MAC, GBP, and RP. And then I save them into the Excel file and then copy it in the text file with the name color underscore without underscore modify.txt. It is a name which I use it here, and then we put all these files into one text file, as you see, mag, GBP, and RP mag Gaia. And now we want to use this file, this magnitude files for what? And this program said that because we have the coordinates, now we have the coordinates from sky, yes? But our measurements was from the instrument, from the telescope. And it means that our magnitude is different from the Gaia magnitude. And because of that, because we use the instrument telescope, the magnitude of the telescope, the coordinates, or not the coordinates, the format of the magnitude of me, my observed object, and the Gaia is different. So I should do the regression to have the same format as Gaia. For this, I use the regression and put it here. Regression coefficients, it give us the regression coefficients, and then it's counted, and then it plots, as you see here. this plot shows the difference. It compares the original magnitude, the mag-u, and the new mag-u that after regression. It's regret from this program. It's regret this formula. It does the regression, and then we plot this graph that compare the original magnitude and new magnitude for mag-u. For UMAG, and then this red line shows as here the difference between them, and it compares them. Here we have the regression coefficients as I copy and paste it here. Also the root square value, and also the root mean square value. Error. Root mean square error. I just do this for myself. You can not have it, but I have it. If there is some problem, then I can see where is the problem. Okay, and then we save this file and then goes through this file. So from this program, we have new mag-u. As I told you, after regression, we put it in the new file with the name new mag-u.txt. And we have it here. It is, as you see, after regression. We did regression with this process, and then we compare the original mag-u and new mag-u after regression, and then we save the file into new mag-u.txt text file, and then now we have this new mag-u. Again, I copy it here and paste it in here. And then I copy the GBP and RP from the previous file, and because there is no difference between them, we just modify the mag-u, not the other ones, and then paste it in the text file. And then I do this, but you cannot do this, no difference. If you wish, you can do this or not, no difference. I just want to have them in the neat, in a clean, better format, which is more easy for me to read them after a while. So, okay, it looks better. And then I save this file again, and the name of the file will be this one, color underline modify.txt. In the same directory as you see. Also, I rename this sheet in Excel file, LibreOffice. Okay, save it, and then I can close this one. I just need this file. So here, and this program, it just show us the plot of the magnitude, the new magnitude and the Gaia GBP and RP magnitudes. And we have this program just for plotting the graphs in different form, different magnitude with each other. And now I can run it. You see, this is our result. This is from U underline RP and BP minus G, this one, and then we have from U minus BP, this the second plot here, and then for the third one, we have this from the third one, BP minus RP and U minus G. And just you see, if you do not do the regression, I see that if you do not do the regression, you have the magnitude, for example, minus 16, minus 14, which is completely wrong. And then after regression, if you do the regression, then you have the correct magnitude. Here is the next one. The fourth one, BP minus RP and G minus RP. And the next one, here, BP minus RP and BP minus G. And this is the plot of all plots together, all 5 plots together. I do it that to see that how will be if I plot all of them together. And then the last one is this one that I plot each of them beside each other. I have all plots in one plot figure. You see, if I did larger, you see that we have here U minus RP vs BP minus G, U minus BP vs G minus RP, BP minus RP vs U minus G, BP minus RP vs G minus RP, and BP minus GP to BP minus G. BP minus RP vs BP minus G. And that's all. I can show you again. You see the magnitude after regression. You can test if you do not do the regression, how will be the magnitude? You see minus 14, 16, 13 magnitude, which is, wrong. So with this, we finished the matching, the whole matching, the whole process. Okay. I can stop sharing. Yes. So with this program that I showed you, the whole process that how you can match the stars with Gaia DR3, I showed you and explained you completely from 0 to 100 that how you can do the process of matching. I hope it will be useful for you. And if you have any questions or if you need any help, please contact me, you can write in the comment in the page in the YouTube channel, and if I know, I will answer you. If I do not know, I ask my supervisor and sponsor or someone else, and then I will tell you the answer of that. If you have any problem or question, please ask in comment. And if you have any suggestions, you can tell me. And now my next process, I did the photometry of all Danish telescope, the clusters, which is more than 200 clusters, open clusters. And then I did the matching the stars with Gaia DR3 for all of the clusters. And then now I explain you that how you can match the stars with Gaia. And for me, it took a long time to write the programs, to know how to write, what to write, mostly about the regression. It took a long time. And then I thought that maybe it's good to share my experience to others, that you won't have this problem and you can do your program, your works much more faster. Because if I knew, I did much more faster. I hope it will be useful for you. My next process is I want to fit I want to do the isochrone fitting for all of my observed clusters, and then I want to see that what will be the result. Okay, I hope it will be useful for you, and see you soon. Bye.